Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you. I'm Philip Emeagwali. For 200,000 years, our ancestors counted only one thing at a time. The invention of parallel processing makes it possible for us to count a billion things at once and thus count a billion times faster. This new mathematical knowledge of how to compute faster is a paradigm shift of tectonic proportions. It's called massively parallel processing. Parallel processing is to mathematics what the theory of continental drift is to geology. Parallel processing is to physics what the theory of evolution is to biology. Parallel processing changed the way we look at the computer. In the field of computer science, the quintessential question is this: what is the grand challenge problem for computer science of the 21st century? My answer is this: the hardest challenge in computing is to invent a supercomputer that is several orders of magnitude faster than any existing supercomputer. And more importantly, to use that new supercomputer in a manner that makes the planet a better place for all beings. My contribution to the development of the computer is this: I discovered that by doing many things at once, 180 years on a computer can be speeded up to only one day on a supercomputer. My discovery of how to do many things at once opened the door to the modern supercomputer. My discovery of a new computer that can do many things at once opened the path to a new computer science. I discovered how to solve the toughest problems arising in physics and mathematics and solve them by solving a million problems at once. I invented the supercomputer that is a new internet de facto. For the next generation, their grand challenge will be to invent their internet as their planetary-sized supercomputer. How are supercomputers used? The parallel supercomputer of today will become the modern computer of tomorrow. Asking about the usefulness of the supercomputer that is an internet is like asking about the usefulness of the computer and the internet. That's like asking, what will the world be like without the parallel supercomputer? Without the parallel supercomputer, there will be no modern computer. A world without the parallel processing computer is a world in which 99 of the 100 processors inside your computer is turned off and you are programming at only 1% of your computer capacity and perhaps achieving only 1% of your productivity level. A world without the massively parallel supercomputer is a world in which fewer discoveries are made. It's a world in which innovation is slowed down. It's a world in which human progress is slowed down. And it's a world in which the computer of tomorrow cannot be invented today, and thus making it impossible for us to create the future. A new supercomputer that cannot parallel process across its 1 million processors is reduced to the stature of an ordinary computer that is powered by only one processor, that is not a member of an ensemble of processors. A new supercomputer that is not parallel processing is like New York City with only one street light on. The parallel supercomputer that will enshroud planet Earth as the internet of the future is where today's science fiction will become tomorrow's non-fiction. That planetary-sized supercomputer hopeful is where humanity's future will take shape. 1 in 10 parallel supercomputers are used to discover and recover otherwise elusive crude oil and natural gas. The remaining 9 in 10 supercomputers are used to solve real-world problems that are similar to extreme-scale general circulation models that are used to foresee otherwise unforeseeable global warming. The invention of the parallel supercomputer is the biggest advance in physics since Newton Galileo. In the decade of the 1980s, I conducted my parallel processing research alone, and I did so because it was a grand challenge problem that was over the heads of others. Inventing the 9 new partial differential equations that I solved across a new internet, that is a new global network of 65,536 processors, was out of the depth of any person whose full-time career was to teach mathematics or physics or computer science. It was clear from the vacant expressions on their faces that my explanations of how I emailed my 64 binary thousand codes and data to and from each of my 65,536 processors was science fiction that went completely way over their heads. In 1989, I was the only full-time programmer of the most massively parallel supercomputer that ever existed. The parallel supercomputer was abandoned for only one reason, namely, it was over the heads of any of the 25,000 vector processing supercomputer scientists of the 1980s and earlier. Parallel processing increases productivity across gigantic industries, from healthcare to transportation, to finance, to business. It's impossible to construct a realistic physical model of atmospheric and oceanic circulations flowing across the surface of planet Earth. It's possible to conduct an extreme-scaled, high-resolution computational experiment that are parallel processed across an ensemble of millions upon millions of commodity off-the-shelf processors that shared nothing between each other, that were tightly coupled to each other, that were identical to each other. Who invented the internet? A discovery or an invention is like the moon. It has two parts, the visible part and the hidden part. For that reason, I am well known, but I am not known well. I'm called a father of the internet because I'm the only father of the internet that invented a new internet. The new internet that I invented was a new global network of processors. Processors that encircled a globe is akin to tiny computers in inverted commas around the earth. I was the first person to theorize and to discover how to solve the toughest problems arising in supercomputing and solve them across that new internet that is a global network of processors that encircled a globe. An invention is something new, such as the massively parallel supercomputer. Prior to my discovery that occurred on the 4th of July 1989, the massively parallel supercomputer was not ranked as the fastest supercomputer in the world. My discovery of practical parallel processing changed the course of the computer from computing only within one processor that was not a member of an ensemble of processors to synchronously communicating and simultaneously computing across millions upon millions of tightly coupled processors that shared nothing between each other. I discovered something out of nothing. I broke a scientific dogma when I discovered that there is no limit to the speed up of the parallel supercomputer. The inventor of the parallel supercomputer is the first person to discover an ensemble of processors and to use it to make the impossible to compute possible to compute. I invented the supercomputer as an internet. The new grand challenge is how to invent the internet as a supercomputer. Back in 1974, the year I began to program supercomputers, parallel processing was scorned as a beautiful theory that lacked experimental confirmation. A supercomputer occupies the space of a soccer field. The modern supercomputer is a tool that enables the mind to go where the eyes cannot see. Back in 1989, I was in the news headlines because I solved the grand challenge problem of computing. I was the first person to figure out how to harness the supercomputing power of a million processors, with each processor akin to a tiny computer. It was a grand challenge problem because asking a person to become the first programmer of that first massively parallel supercomputer was like asking a man who had never climbed a mountain to climb Mount Everest. I was the first massively parallel processing supercomputer scientists to record the fastest speed in computing. To record the fastest recorded supercomputer speeds and to record them across a new internet that demanded that I visualize my emails as exploding across my new internet. I visualize emails as exploding like bullets out of my eyes. I was asked to describe the Philip Emeagwali formula for inventing the fastest supercomputer that then US President Bill Clinton referred to in his White House speech of August 26, 2000. Back in 1989, the vector processing supercomputer lost its practical merit because it became obsolete and it no longer underpins the fastest computer or supercomputer. The starting point of my contribution to the development of the world's fastest computer was the science fiction story about 64,000 human computers communicating and computing together and doing both to solve the grand challenge mathematical problem of extreme scale weather forecasting, and do so by mathematically reformulating that tough problem as 64 binary thousand initial boundary value problems. I am the extreme scale computational mathematician that invented the Philip Emeagwali formula that then US President Bill Clinton spoke about. The Philip Emeagwali formula was how I reformulated a grand challenge problem of mathematical and computational physics and reformulated it from a mathematical model on my blackboard to 64 binary thousand computational models that I parallel processed and executed across as many motherboards or processors or computers. I was in the news headlines because I invented practical parallel processing. That invention occurred on the 4th of July 1989 and occurred across a new internet that was outlined by 2 raised to power 16 commodity processors that I simultaneously harnessed and that encircled a globe as a global network of processors and that encircled that globe in the 16th dimensional mathematical space and that encircled that globe in the manner the internet that is also a global network of computers encircled planet Earth. I was the first person to lecture on the first algorithm for processor-to-processor processing and solution of real-world problems. And I was the first person to present a series of step-by-step instructions for solving the toughest problems that the supercomputer attracts. For many years, I helped many research mathematicians, research computational physicists, and research supercomputer scientists, and I helped them to solve difficult problems that they could not solve. None of them even acknowledged me in their grateful thanks list. That lack of acknowledgement is one of many subtle ways the contributions of the black inventor gets discredited. It's one of the ways black inventors get oppressed. It's one of the ways the narrative of black contributions to human knowledge gets erased. After those trials and tribulations, I knew to keep the credit for my discovery of practical parallel processing that occurred on the 4th of July, 1989. Keeping the credit for my invention was simple. First, I refused to immediately teach vector processing supercomputer scientists how to parallel process across an ensemble of 64 binary thousand processors. Second, I only talked to the award committee of the Computer Society of the IEEE that gives the top prize in the field of supercomputing. That supercomputing committee reviewed my discovery of practical parallel processing and did so entirely by interviewing me on the telephone and by long-distance correspondence, and did so without knowing that I was black and African. The way I looked at the computer changed at 8:15 in the morning of July 4, 1989. The breakout moment I discovered that the slowest processors in the world could be harnessed and used to solve the toughest scientific problems in the world, and used to solve them faster than the fastest supercomputer in the world. In the old way, and before my invention, we thought of the supercomputer as computing only one thing at a time, and computing that thing with only one vector processor. In my new way, and after my invention, we think of the supercomputer as computing many things at once, and computing those things with millions upon millions of processors that were identical to each other, that were tightly coupled to each other, and that shared nothing between each other. That is, I experimentally discovered how and why the modern supercomputer must compute in parallel in order to simultaneously solve millions upon millions of the most grand challenging problems arising in physics and mathematics, instead of solving only one grand challenge problem at a time. After my invention, the number of parallel supercomputers exploded. Before my invention, parallel processing was scorned, ridiculed, and rejected as a beautiful theory that lacked an experimental confirmation. To discover or invent the massively parallel supercomputer is to make the impossible to compute possible to compute. Please allow me to do a retrospective on the supercomputer back in 1974 and today. I began supercomputing on June 20, 1974, and as a 19-year-old at 1800 Southwest Campus Way, Corvallis, Oregon, United States. As a 19-year-old supercomputer programmer, I felt like a small boy that was in charge of a big ocean liner that turned slowly. At age 19, I was like a mouse crawling inside the supercomputer. By age 34, I had grown into the lion that was protecting the supercomputer hopeful that will be massively parallel processing across my ensemble of 2 raised to power 16 commodity off-the-shelf processors. The supercomputer is getting bigger each year and now costs the budget of a small nation. One supercomputer costs up to $1.25 billion. If this trend continues, the supercomputer might eventually become as big as planet Earth and as costly as the budget of the United States. The supercomputers that I programmed back in the 1970s and 80s could fit into a small bedroom. when it comes to supercomputing, size matters. Today, the massively parallel supercomputer is such a success story that the modern supercomputer now occupies the space of a soccer field. Supercomputing is a big science project that is at the level of the International Space Station. The fastest supercomputer can be at the level of the ITER project that is built in southern France. ITER is the world's largest fusion experiment that is funded by a consortium of 35 nations. ITER is hoped to prove the feasibility of fusion as a source of energy. ITER stands for International Thermonuclear Experimental Reactor. The fastest supercomputer of the future could cost as much as the super collider that was built by the European Organization for Nuclear Research called CERN. In the 1980s and earlier, the big question in the world of the supercomputer was this: can an ensemble of the slowest processors outperform the fastest supercomputer and change the way we look at a modern computer? I answered that grand challenge question by visualizing my parallel supercomputer not as a computer per se, but as a global network of processors that is an internet de facto. I answered that grand challenge question by discovering the supercomputer's inner map and its email GPS. I discovered how millions upon millions of tightly coupled processors must work together as a whole to solve the toughest problems arising in physics and mathematics. I deciphered the email pathways across 1 binary million email wires. Knowing that email pathway is a mathematical precondition to executing the fastest supercomputer speeds. That supercomputer quest was my expenditure to the outer limits of algebra, to the outer limits of calculus, and to the outer limits of the computer. The new big question in the world of the supercomputer should be: can an ensemble of all the processors in the world be harnessed as one cohesive, seamless, fastest supercomputer and change the way we look at the modern supercomputer? The biggest question in computing is how to invent a cosmic supercomputer that encircles the Earth and that is powered by all the computers on the Earth. You may wonder, what is the answer to that biggest question? My answer is this: if anyone knows the answer to the biggest question in computing, then it wouldn't be an unanswered question. To discover demands that I become reclusive and that I look inwards and go inside and do them with my scientific sixth sense. To discover that my ensemble of 2 raised to power 16 processors is a new internet demands that I visualize the configurations of its 1 binary million bidirectional email wires, and that I visualize my ensemble in the 16th mathematical dimension, and that I look into a deep unseen universe. that is at the jagged frontier where physics, mathematics, and supercomputing meets. The reason Nigeria needs far more research scientists than the United States is that the Nigerian scientific discoverer will be drafted as a soldier in Africa's fight against poverty and for humanity's quest for progress. In supercomputing research, the highest recognition is to contribute new knowledge that makes computers faster and makes supercomputers fastest. Or to invent something such as the parallel supercomputer that is an internet de facto. In the 1970s and 80s, it was a grand challenge to define myself within the social expectation that I could not win the top prize in the field of supercomputing. It was a grand challenge to defy the racial stereotype that I could not solve the grand challenge problem of computing and solve it alone. In 1989, I experienced a severe negative backlash, and I was attacked for discovering practical parallel processing and thus for making my contribution to the development of the computer and to mathematical knowledge. The debates about Philip Emeagwali were never about the 9 partial differential equations that I invented or about how I figured out how to harness the new parallel supercomputer and how to use it to solve grand challenge problems arising in mathematical and computational physics. The debates were about the black inventor, not about his race-neutral invention. We have black mathematicians, but there is no such thing as black mathematics. So the controversy was about the black inventor, not his invention. Solving the toughest problem arising in mathematics is not about making the list of the 10 most intelligent persons that ever lived. As a black inventor, making my invention was an accumulation of the right factors that included making myself invincible and doing so to minimize racial prejudices. As a black and a sub-Saharan African born, winning a top scientific prize of the Western world and winning it alone put me in a privileged position that was previously reserved for prominent white scientists such as Albert Einstein. In 1989, if it was known in advance that I was black and born in sub-Saharan Africa, I certainly would not have won the highest award in the field of supercomputing. Back in 1989, many newspapers dropped the story of my discovery of parallel processing and did so after they discovered that I was black and sub-Saharan African. The school is where future scientists learn the stories of scientific discoverers that contributed to human knowledge and that changed the world. A school should de-emphasize the promotion of political and religious figures who did not contribute to the knowledge that is in the school textbook, but should emphasize the promotion of scientific and technological figures that contributed to the knowledge that is in the school textbooks. In Africa, every teenager can name a few pastors or imams, or at least Jesus Christ or Mohammed or the Pope. but it is the rare African teenager that can name a major scientific figure that contributed to the development of the computer that he or she uses every day. In that regards, I was the first African-born scientist that contributed to science that appeared on 2 Nigerian postage stamps. That should not come as a surprise because the United Kingdom and the United States and every nation in the world has used its postage stamps and or currencies to communicate its contributions to scientific knowledge and to human progress. According to the United Nations, 65 million persecuted refugees were forced to flee from their homes and forced to flee from civil wars and forced to flee from areas that were afflicted with severe food shortages. For the last 3 years of the late 1960s, I was a refugee in Biafra, a breakaway nation in the southeastern region of Nigeria. In Biafra, we lived in former classrooms that were converted into living rooms. For 3 years, all schools in Biafra were closed and converted into makeshift overcrowded housing and feeding centers for millions upon millions of Biafran refugees. I was a child soldier on the Biafran side of the Nigeria-Biafra War, a war that raged during the last 30 months of the 1960s, a war that was described as Africa's bloodiest war, and a war in which 1 in 15 Biafrans died. My journey to my invention was a 20-year-long journey that began at a war front in July 1969 and ended 20 years later at the frontier of knowledge on the 4th of July 1989. The turning point in my journey to the frontier of the most massively parallel supercomputer occurred 20 years before my experimental discovery of the massively parallel supercomputer that in turn occurred on the 4th of July 1989 and occurred in Los Alamos, New Mexico, United States. In July 1969, I was conscripted as a 14-year-old soldier and sent to the Oguta War Front, Igbo land, Biafra, West Africa. I was conscripted at gunpoint into a war that was on par with the American Civil War or the Spanish Civil War. I was the youngest soldier at the Oguta War Front, Biafra. That war turned my ancestral hometown of Onitsha, Biafra, into Africa's bloodiest battlefield. I arrived at the Oguta War Front and arrived a few days after 500 Biafran soldiers fell on the ground. 500 soldiers fell as if they were dry leaves. I was conscripted to replace one of the 500 men that died. At the Oguta War Front of Biafra, there were more guns than pens. That 30-month-long war ended on July 15, 1970, and ended with the defeat of Biafra. In mid-1968, my postal address was the refugee camp at St. Joseph's Secondary School, Oketiti, Biafra. My family of 9 lived in a tiny classroom of St. Joseph's Secondary School. In Biafra, West Africa, all schools were closed from June 1967 through early 1970. Schools in Biafra were closed because they were either located at the war front or closed so that refugees like those of us that fled from Asaba and Onitsha could live in its classrooms. In Biafra, all school classrooms were reconfigured as living spaces for refugees and soldiers. The refugees at St. Joseph's had no chairs, no tables, no beds. Refugees slept on a mat that was spread across the concrete floor, and many slept on bare floors. My father, Nnameka James Emeagwali, who was appointed our refugee camp nurse, said that most refugee children, including my youngest brother, had kwashiorkor. Kwashiorkor is a nutritional disorder that is caused by the lack of protein. Kwashiorkor was prevalent in famine-stricken Biafra at St. Joseph's refugee camp. There were days I only ate palm kernels and fried cassava flakes called gari. By mid-1970, and 6 months after the war has ended, I was still living in refugee quarters along Port Harcourt Road, Fege, Onitsha, East Central State, Nigeria. Each morning, I took an empty bucket to fetch water from the eastern bank of the River Niger. Port Harcourt Road was a short walk from the banks of the River Niger. Fast forward 4 years from that refugee quarters in Fege, Onitsha, I was in Monmouth, Oregon, in the Pacific Northwest region of the United States. I'm often asked to describe my scientific struggles. From the 1960s through the 80s, parallel processing was the subject of a titanic battle between the majority, who believed that all supercomputers should be powered by a single isolated processor, and the minority, who believed that all supercomputers should be powered by an ensemble of processors, or maybe millions of processors. Countless dismissive statements were made about supercomputing in parallel. That was why only one computational mathematician attended my public lecture on parallel processing that took place in November 1982 in a lecture auditorium that was a short walk from the White House, Washington, D.C. I'm often asked to explain how I invented a new supercomputer. Making a technological invention demands an intercourse between the sciences and demands the exchange of fluids, or rather the exchange of knowledge. That exchange is a necessary condition to making a scientific discovery. Scientific babies or new discoveries come from a respectful and joyous exchange of fluids. For me, Philip Emeagwali, that exchange of new knowledge occurred at the crossroad where physics, mathematics, and computer science met, and occurred on my eureka moment of 8:15 in the morning of the 4th of July, 1989. That crossroad was where I made the invention that opened new possibilities in supercomputing. The 9 Philip Emeagwali equations are my contributions to calculus. Back in 1970, at age 16 at Christ King College, Onitsha, East Central State, Nigeria, everybody knew me by my nickname, Calculus, and nobody knew my real name, Philip Emeagwali. calculus is a tool that enables the mind to go where the eyes cannot see. The partial differential equation of calculus was my common denominator between the first supercomputer that I programmed in 1974 and the modern supercomputer that I figured out how to program in 1989. Between the ancient laws of physics and the modern laws of computing, the partial differential equation of calculus is the pink elephant in the room. In supercomputing, calculus is the uncle nobody in the family wants to talk about. In a literal sense, and as a research mathematician, calculus is my mother tongue, not the Igbo language that my mother spoke. I have written 1,000,000 pages on the partial differential equations of calculus and written them from my blackboard to my motherboard and across my two raised to power 16 commodity off-the-shelf processors that were tightly coupled to each other. I also invented algorithms that I used to solve the toughest problems in calculus. In contrast, I cannot write a letter in my ancestral Igbo language. Parallel processing is a disruptive technology that displaces sequential processing, a technology that in turn established itself for half a century. Searching for the parallel process solution to the toughest problem arising in calculus and physics was like searching for a black goat at night. My scientific journey to the farthest frontier of technological knowledge and my quest for the fastest supercomputer that is a new internet was a mathematical journey from fiction to fact to forecast. The fastest supercomputer is where humanity's future takes shape. The computer is the greatest invention since fire. The modern supercomputer is the greatest invention in computational physics. I believe that we are witnessing a technological change of tectonic proportion. Of course, every citizen scientist had discovered or seen something that nobody else had previously seen. But those citizen scientists will not be rewarded with the immortality of Isaac Newton and Galileo Galilei. They will be rewarded if and only if they discovered something that is both groundbreaking and paradigm shifting. The contribution to human knowledge that makes the news headlines has to be a groundbreaking invention like a new computer or a new internet or the cellular phone, and has to be something that is used every day and used by everyone and studied by school children for hopefully the next 1,000 years. This is difficult because many people don't think beyond their 100th birthday. I was asked, what were the religious influences or your contributions to science? My family had eclectic religious belief. We, the children, were Christians. My mother was an animist, but proclaims to be a baptized Christian. And my father was an animist who was baptized and trained in Christian schools, but only claims to be a mystic of the Rosicrucian order. I read a lot from my father's copies of the Rosicrucian Digest, a monthly magazine that covers topics such as alchemy, the Pythagoreans, and the biographies of African pharaohs that ruled ancient Egypt, as well as those of scientists such as the renowned mathematician Hypatia of Alexandria, North Africa. I was the first person to witness the transition from the computer that solved one problem at a time to the modern computer that solves many problems at once. The first programmable computer was invented in 1946. That first supercomputer weighed over 30 tons or 60,000 pounds, or the weight of 400 persons that each weighed 150 pounds. That first supercomputer had about 18,000 vacuum tubes. That supercomputer was outdated the following year with the invention of the transistor in 1947. The integrated circuit was invented 11 years later in 1958. Since 1946, the supercomputer burned in the sky like the sun. 31 years after the integrated circuit was invented, and on the 4th of July 1989, I became the first person to discover that an ensemble of the slowest processors in the world can work together to compute faster than any supercomputer. That discovery inspired the development of the modern supercomputer that massively parallel processes to solve the toughest problems arising in STEM fields. The parallel supercomputer is to physics and mathematics what the telescope is to astronomy, or the microscope is to biology. The parallel supercomputer was science fiction to Albert Einstein, who presumably read about it but as a futuristic technology, and read about it in his local newspaper, namely the January 11, 1946 issue of the New York Times that reported on how 100 computers could forecast the weather all over the world. That New York Times article suggested that in the future, and I quote, the United States would be divided into blocks penetrating into the stratosphere. End of quote. Fast forward 43 years to the 4th of July 1989, I discovered how to divide the United States into 64 binary thousand blocks, each penetrating into the stratosphere. I invented how to achieve a one problem to one processor mapping between those blocks and between as many tightly coupled processors. I discovered how to reduce 64 binary thousand days or 180 years of computing to merely 1 day of supercomputing. I discovered a new way of thinking about the new fastest supercomputer and about the supercomputer of tomorrow, not as a computer per se, but as a global network of processors that were identical to each other, that were tightly coupled to each other, that shared nothing between each other. That is a virtual supercomputer de facto. The invention of a faster supercomputer is a milestone of human progress. It made some impossible to solve problems arising in physics, algebra, and calculus possible to solve. Who invented the internet? The internet has many fathers and mothers, as well as aunts and uncles. But only one father of the internet invented a new internet. The father of the internet should at least contribute new technological knowledge that pertains to the internet and do so by inventing a new internet. I am called a father of the internet because I am the only father of the internet that invented a new internet. I invented my new internet by first theorizing it on my drawing board. I drew my new internet as a new global network of 64 binary thousand processors that I also visualized as a virtual supercomputer. After 15 years of conducting research at the farthest frontiers of knowledge in algebra and calculus, I developed the intuitive feeling that I could figure out how to solve the grand challenge problems of supercomputing and solve them by parallel processing them across a new internet. After those 15 years, I developed my intuition on how to record the previously unrecorded speeds in supercomputing that I recorded back on July 4, 1989 in Los Alamos, New Mexico, United States. That supercomputing achievement was why I was in the news headlines for discovering how to compute fastest and do so across a new internet. The record supercomputer speeds that I visualized were how to execute a humongous set of floating point arithmetical operations and how to execute them 65,536 times faster, and how to execute them across my new internet that is a new global network of 65,536 or 2 raised to power 16 commodity off-the-shelf processors. Each of those 64 binary thousand commodity processors were identical to each other and were equal distances apart from its 16 nearest neighboring processors. I visualized my 2 raised to power 16 processors as etched across the 15-dimensional mathematical hypersurface of a hyperglobe that I also visualized in the 16th dimensional hyperspace. I allowed my intuition to guide me, in part because I visualized how I could record speeds in email communications and do so to and from each of those 65,536 processors. I visualized how to execute and record email speeds that will be 16 times 2 raised to power 16 or 1 binary million times faster, and how to do so across my new internet that was outlined by my new global network of 1,048,576 email wires that I visualized as mutually perpendicular at 2 raised to power 16 points on the surface of my hyperglobe. After 15 years of supercomputing that was onward of June 20, 1974 in Corvallis, Oregon, United States, I developed an ability to understand how to massively parallel process across millions upon millions of processors. That decade and a half supercomputing experience gave me the confidence to attempt solving grand challenge problems that other supercomputer scientists shied away from. I solved the grand challenge problem of computational mathematics because I was able to metaphorically visualize it around a globe in 3-dimensional space. I visualized that globe as representing planet Earth that was enshrouded with fluids, namely the oceans and atmosphere. And I was able to visualize a second hyperglobe in the 16th dimensional hyperspace. That hyperglobe was also encircled with 2 raised to power 16 processors. Comparing both globes and their associated global networks of tightly coupled processors was akin to comparing a circle that circumscribed a square to a sphere that circumscribed a cube. As an aside, the inspiration for my new supercomputer first entered into print as a science fiction story that was dated February 1, 1922. In that science fiction story, 64,000 computers solved the initial boundary value problem of mathematical physics that governs the flow patterns of the weather around planet Earth. Back in 1922, the word computer referred to a person that calculates. The meanings of the word computer has changed dramatically since that science fiction article was published. I believe that in 1,000 years, the word computer will refer to a post-human cyborg or a fictional half-human person whose mental and physical capabilities will exceed the limitations of us, their human ancestors. Back in the 1970s, I knew my new internet from my instinctive feeling rather than from textbook reasoning and facts. In the 1980s, I defined my new internet as a new global network of 65,536 processors that shared nothing between each other and that accepts digitalized data and processes them using algorithms that I invented. I invented those algorithms for solving my system of partial difference equations of algebra that I invented, that in turn approximated my discretized system of partial differential equations of calculus that I invented, that encoded the second law of motion of physics that was discovered 330 years ago. The laws of physics are encapsulated in this system of equations. The partial differential equation form the backbone of computational fluid dynamics. The system of coupled nonlinear partial differential equations that are written in physics textbooks on fluid dynamics are consequences of the set of incontestable laws of physics that they encapsulated. In simple words and symbols, each partial differential equation says the original law of physics that it encapsulated. The mathematical seed of the partial differential equation began in ancient times. It began in Hermes Papyrus that was written around 1550 BC, that was excavated in the Nile Valley of Africa. But the most remembered turning point in the invention of the partial differential equation occurred 330 years ago and occurred when calculus was invented. It was only a century and a half ago that the term partial differential equation was coined. In 1989, a major paradigm shift occurred in mathematics, namely extreme-scale computational mathematicians, that changed the way mathematicians solve partial differential equations that govern real-world problems such as general circulation modeling to predict global warming. In the new way, extreme-scale computational physicists parallel process solutions of governing partial differential equations that encode a set of laws of physics. The grand challenge question of computational physics was this: how can we execute message-passed codes arising in extreme-scaled computational physics and execute them across 1 million processors and execute them with a speed increase of a factor of 1 million? Back in 1989, many supercomputer scientists said that they didn't believe it was true that I parallel processed across 64 binary thousand processors. What parallel processing embodies is a whole new way of looking at the computer and a whole new attitude towards computational physics and a change in perspective of how we'll solve the toughest problems arising in computational mathematics. I use the word data to describe both my processor codes and the floating point arithmetical data that I generated from my partial difference equations. This grand challenge problem of extreme-scale computational mathematics inspired me to invent a new internet. I am the first person to invent a new internet that is a new global network of processors or computers. The magnetic north of the story of how the internet was invented is different from the true north of how it was invented. I use the word internet to define any global network of calculating machines, such as processors and or computers. 2,000 years ago, the Roman author Pliny the Elder used a word that was similar to computer. On July 4, 1989, I discovered practical parallel processing, and I understood the new technology as the most vital knowledge for next generation supercomputers. Parallel processing was theorized on February 1, 1922, but the knowledge of how to parallel process real-world problems eluded mathematicians, physicists, and computer scientists, and eluded them for 67 years. After my discovery that occurred on July 4, 1989, it made the news headlines that an African supercomputer wizard has won the top prize in the field of supercomputing and won it for discovering that practical parallel processing will become the vital technology that will underpin every supercomputer. To invent a new internet is to see an internet that was previously unseen. In the 1970s, I saw two previously unseen internets. My first new internet was a small copy of the internet. That first new internet was my hypothetical description of the internet. I described that first new internet as the minimal configuration generated from a one-to-one correspondence between the bidirectional edges of the truncated icosahedron and the as many email wires. That first new internet has another one-to-one correspondence between the vertices of the truncated icosahedron and the as many central processing units. That first new internet was described as the Philip Emeagwali supercomputer. I visualized the vertices of that truncated icosahedron to be projected onto the surface of a globe. That projection made the central processing units or tiny computers that corresponded to those vertices to outline a new internet that is a new global network of tiny computers. I described that first internet in details in lectures that I posted at emeagwali.com. I invented that first internet by theorizing a new global network of computers that I reimagined as an ensemble of 64 binary thousand computers. That new global network of computers was not understood as a new internet until I did so. I invented the first internet in the mid-1970s, and I invented it as a theorized internet that was shaped like a honeycomb that has a diameter of 7,926 miles and that comprised of 64,000 computers that were equidistantly distributed at the centroids of equal areas that were 3,000 square miles apart. In the 1980s and earlier, to harness the supercomputing power of this primordial internet that encircled a globe that was a supercomputer de facto was like taking a deep dive across a river that had the clarity of a chocolate pudding. I invented a second internet in 1982. I programmed that new internet in the 1980s. I visualized my new global network as 2 raised to power 16 commodity off-the-shelf processors that were identical to each other, that were tightly coupled to each other. I visualized each processor as operating its own operating system. I visualized each processor as having its own dedicated memory that shared nothing with each other. I visualized my new internet as outlined by the 1 binary million bidirectional edges that were defined by the 64 binary thousand vertices of the 16-dimensional hypercube that was tightly circumscribed by a 16-dimensional hypersphere that was embedded into a 16-dimensional mathematical hyperspace. I mathematically visualized my 16-dimensional internet as occupying the space of a soccer field rather than encircling planet Earth that has a diameter of 7,926 miles. I mathematically visualized my 16-dimensional internet as outlined by 64 binary thousand identical processors or as many tiny identical computers. I visualized those tiny computers to be uniformly distributed across the 15-dimensional hypersurface of the hypersphere in hyperspace. I mathematically visualized those tiny computers that defined my 16-dimensional internet as braided together by one binary million email wires that were orthogonal to each other and that were perpendicular in 16 directions and in as many dimensions. I was recognized for inventing two new internets because the two internets that I invented were previously unseen and unrecognized as internets. I'm Philip Emeagwali. I am the only father of the internet that invented a new internet. The inventor sees her invention first within her mind before seeing it with her eyes. In the 1970s and 80s, I saw and programmed my 16-dimensional internet, and I did so when 25,000 supercomputer scientists only saw a network of 2 raised to power 16 or 65,536 central processing units that could not be programmed to solve as many challenging problems, but also could not be programmed to reduce 65,536 days or 180 years of time to solution on only one computer to only 1 day of time to solution across that new supercomputer that is not a computer per se, but that is an internet de facto, and that is a virtual supercomputer. But inside my mind, I saw a new internet, and I did so where 25,000 supercomputer scientists saw an old computer. Merely seeing something that was never before seen and only seeing that thing with our eyes is not discovering that thing. It is seeing something that was never before seen and seeing that thing inside our minds and understanding that thing that was previously misunderstood that leads to the scientific discovery of that thing. I saw a new internet that was never before seen. I saw that new internet inside my mind. My new internet was not understood as a computer or as an internet. I invented a new supercomputer that is also a new internet de facto. I am the only father of the internet that invented a new internet. I'm Philip Emeagwali. My 16-dimensional internet was as minimal as a sphere, but yet as delicately complex as a parallel supercomputer. I figured out how to program my internet and do so via email messages that I sent to and received from my 16-bit long email addresses. I was the lone and the first supercomputer programmer to visualize his parallel processed codes as transported along email pathways that had a one-to-one correspondence with the bidirectional edges of the hypercube in 16-dimensional hyperspace. I combined that 16-dimensionality with the computer algorithm that I used to solve my 24 million algebraic equations. In the 1980s, that was the world's largest system of equations ever solved. I integrated my 64 binary thousand processors into one synchronized, harmonious, and seamless supercomputer that executed the fastest calculations and did so while solving grand challenge problems that arose in mathematics, science, and engineering. I visualize my internet in the 16th dimension. I visualize the data called the initial and boundary conditions of the initial boundary value problem of calculus, and I visualize them differently and as 65,536 sets of initial boundary value problems. In contrast, other research mathematicians and supercomputer scientists visualize the same grand challenge problem as merely one problem. I visualize each initial boundary value problem in the 16 perpendicular directions of the 16-dimensional hyperspace. In science fiction, the hyperspace is a fictional space in which extraordinary events can happen. On the 4th of July, 1989, one such extraordinary event happened, and did so when I parallel processed across a 16-dimensional hyperspace to discover the world's fastest computer that was outlined by 2 raised to power 16 processors. The science fiction that became my reality was once the cover story of the January 11, 1946 issue of the New York Times. That issue of the New York Times described parallel processing as simultaneously solving 100 mathematical physics problems and solving them with 100 computers that could forecast the weather all over the world. Back then, in 1946, one computer weighed as much as 400 persons. That New York Times article of 1946 suggested that in the future, and I quote, the United States would be divided into blocks penetrating into the stratosphere. End of quote. Fast forward 43 years to the 4th of July 1989, I figured out how to parallel process by dividing the United States into 64 binary thousand blocks, each penetrating into the stratosphere. My discovery of parallel processing, or emailing and solving a million problems at once, was later highlighted in the June 20, 1990 issue of the Wall Street Journal. 11 years later, my invention of a new supercomputer was reconfirmed by then US President Bill Clinton and reconfirmed in his presidential lecture of August 26, 2000 that was delivered to the Nigerian Parliament in Abuja, Nigeria. In my vision across hyperspace, my email messages flew like a swarm of 16 colored birds. I visualized my emails dancing across every nook and crevices of my 1 binary million email wires. I imagined that someday those forests of processors or tiny computers and email wires could encircle the earth in the way the atmosphere enshrouded the earth. I, the supercomputer programmer, parallel processed across the 16th dimension. I parallel processed by trying to twist and fuse together the bidirectional edges and vertices of the hypercube that I projected onto the hypersurface of a hypersphere. I parallel processed by using email techniques that reduced my 64 binary thousand processors that tightly encircled a globe that shared nothing to one seamless cohesive supercomputer that is the world's fastest computer. In supercomputing, I possess the secret sauce or the new knowledge that enabled me to invent the world's fastest computer. In computational physics, a necessary condition for solving a grand challenge problem that is computation intensive is that I must correctly visualize how to massively parallel process that problem and process it as a million smaller problems and process it across as many tightly coupled processors. A second condition for inventing the world's fastest supercomputer is that I must correctly visualize how to send and receive each problem across a new internet, that is a new global network of 65,536 central processing units. A third condition for inventing the world's fastest supercomputer is that I must correctly visualize how to parallel process all those problems and how to send and receive each problem to a processor and how to compute with a one-to-one correspondence that maintains nearest neighbor problem to processor mapping. A fourth condition for inventing the world's fastest supercomputer is that I must correctly visualize how to maintain the connectivity of 65,536 problems and codes on as many identical memory units and on as many identical central processing units that were each in close proximity to its 16 nearest neighboring central processing units or tightly coupled processors that shared nothing. Most importantly, I must understand that my invention of the parallel supercomputer was a paradigm shift. Parallel processing was a quest for a new direction in the world of the supercomputer and the internet. My quest for a new direction led to my experimental discovery of how and why parallel processing across a new global network of 65,536 processors or across a new internet reduced 65,536 days or 180 years of time to solution on only one processor that is not a member of an ensemble of processors to just 1 day of time to solution across a new internet that is a new global network of 65,536 commodity off-the-shelf processors. Back in 1989, I was in major US newspapers for my contributions to the development of the supercomputer. I was described as the Nigerian supercomputer genius that discovered that parallel processing makes computers faster. That supercomputer genius resided in my ability to visualize my new internet as having 16 sets of email pathways that each contained 2 raised to power 16 paths. That supercomputer genius was in my visualizing and associating a unique color to each set of email pathways. Those 16 colors enabled me to identify both on my storyboard and on my blackboard each member of my 16 sets of 65,536 paths. That supercomputer genius was in my visualizing those 16 sets as perpendicular pathways that were orthogonal to each other and that we are pointing to 16 mutually perpendicular directions in 16-dimensional hyperspace. Most vector processing supercomputer scientists work as part of a multidisciplinary team of up to 1,000 mathematicians, physicists, and computer scientists. For that reason, the modern supercomputer scientists don't have to know nearly everything about the supercomputer. In contrast, the supercomputer scientists of the mid-1940s knew nearly everything about the supercomputer of that era. As a lone supercomputer scientist who came of age in 1974, my grand challenge was to figure out how to harness my ensemble of 64 binary thousand tightly coupled processors that shared nothing. That is, each processor operated its own operating system, and each processor had its own dedicated memory. My grand challenge was to figure out the intricate one-binary million pathways of the email messages that I was sending to and receiving from my 16-bit long email addresses. My grand challenge was to visualize my new internet not simply as a new global network of processors that was mathematically embedded within the 16th dimensional hyperspace, but also as 65,536 tightly coupled processors that were connected to each other as one cohesive unit that is both a new supercomputer and a new internet de facto. That new internet that is a new supercomputer is a network of networks that was 16 networks deep, but yet in 3-dimensional physical space and in 16-dimensional mathematical space. That is, my grand challenge was to know a priori and know from my theoretical deductions that my internet connections were along 16 directions that were perpendicular to each other and that were in my theorized 16-dimensional hyperspace. My grand challenge was to discover that my new ensemble of processors defined a new internet. I discovered practical parallel processing as the vital technology that must underpin every supercomputer, and I discovered it before I could harness that new global network of processors as a new internet. As its first programmer, I had to understand my new internet as a network of networks that is 16 networks deep and thoroughly understand that invention before I could take the next step of programming the new internet to send and receive my emailed grand challenge codes and receive them at 2 raised to power 16 or 64 binary thousand processors. Each of those processors had its unique 16-bit long binary identification number that jointly served as its unique email address. As the first programmer and the first massively parallel supercomputer scientist, I did not learn the modern supercomputer that do many things at once. What made the news headlines back in 1989 was that a Nigerian supercomputer genius in the United States had figured out for the first time how to solve 65,536 real-world grand challenge problems. and how to solve them at once and solve them across a new internet that is a new global network of as many processors. I, Philip Emeagwali, was that Nigerian supercomputer scientist that was in the news back in 1989. After 16 years, I knew the positions of the processors that defined the Philip Emeagwali internet. I knew them, both forward and backward, and I knew them along 16 directions that were orthogonal to each other. A secret source to my recording of the world's fastest computation and to my inventing of the fastest parallel supercomputer is that I discovered how to preserve the proximity of my 64 binary 1000 supercomputer codes to the proximity of the corresponding initial boundary value problems of extreme scale computational physics. I discovered how to preserve that proximity and how to do so, and I discovered it when I mapped codes to tiny computers called processors, and when I emailed those codes in a one code to one processor corresponded way. That is, I emailed 65,536 grand challenge problems in parallel supercomputing to as many processors. On the 4th of July 1989, I figured out how to email supercomputer codes so that real-world problems that were nearest neighbors on the earth and that shared boundaries were sent to processors that shared nothing, or tiny computers that were nearest neighbor on the surface of a globe in hyperspace. I thought of my one-to-one corresponded problem to processor mapping this way. My country of birth, Nigeria, has Cameroon, Chad, Togo, and the Atlantic Ocean as its nearest neighbors. For this proximity, the extreme scaled general circulation model, that is a grand challenge problem of physics that is executed across my massively parallel supercomputer, must assign 16-bit long email addresses to Nigeria, to each neighboring country of Nigeria, and to the Atlantic Ocean that bounded Nigeria. My eureka moment occurred when I figured out that Nigeria's 16-bit long email address must differ in only one bit position from the email address of its nearest neighboring countries and the bounding ocean. Loosely speaking, I applied that same addressing scheme of 16-bit long email addresses that differed in only one bit position to all rivers, lakes, and oceans and mountains that I must account for within the general circulation model that must be used to foresee otherwise unforeseeable global warming. By the 4th of July 1989, I had figured out how to uniquely name each of my 64 binary 1000 processors, or as many tiny computers that outlined my new internet. I named my tiny computers recursively, not randomly, as I had presumed in the mid-1970s when I began my quest for the ensemble of the slowest processors in the world that I could invent as the fastest supercomputer in the world. My unique naming strategy that yielded my 64 binary 1000 or 2 raised to power 16 unique 16-bit long names was as follows. I began with 2 ensembles of tightly coupled processors that shared nothing and that contained the same number of processors or tiny computers that had identical names. For example, my two ensembles of 32 processors were each named by 32 unique strings of zeros and ones. I append 0 as the first name of every 32 processors in the first ensemble, and I append 1 as the first name of every 32 processors in my second ensemble. I visualize those two sets of tiny computers as quote-unquote brothers. I call them brothers because I assign them different first names, but I assign them the same last name. Newspapers that profiled me when I won the top prize in the field of supercomputing and won it in 1989 gave me the nickname, quote-unquote, the African supercomputer wizard. I was called a genius because I was the first person to figure out how to program those 64 binary thousand tightly coupled tiny computers that shared nothing. What made the news headlines was that I figured out how to harness the potential or untapped supercomputer power of my 65,536 computers, tiny computers. I visualized those slow computers as encircling my internet and doing so in a manner that was metaphorically akin to my flying 65,536 grand challenge codes and to my flying those computer codes through as many tiny computers and to my flying them while I was blindfolded. My wizardry resided in the technological achievement that I did not need to see any of the 65,536 tiny computers that I used to invent the world's fastest supercomputer. I physicalized the world's fastest supercomputer, and I did so without using my biological eyes to see any of its processors, and I did so without using my fingers to touch any of its processors. Because I was programming a record number of processors and doing so blindfolded, I had to have some concrete metaphors that I associated to that never before programmed supercomputer hopeful that was a new internet de facto. I drew my metaphors from my life experiences. Back in the 1980s, I quote-unquote mapped about my 32 closest blood relatives from the same house in my ancestral hometown of Onitsha, Nigeria, to the same house in my adopted hometown of Washington, District of Columbia, United States. If I had mapped each of my 32 relatives to 32 different states, they will not have the nearest neighboring communication that they needed to do well in the United States. That nearest neighbor metaphor inspired me to do the same with my ensemble of processors that was a group of 65,536 tightly coupled processors that were identical and that shared nothing, and that I viewed as one seamless, cohesive supercomputer. What made the news headlines was that on the 4th of July 1989, I discovered how that ensemble becomes the world's fastest supercomputer. I discovered how the fastest computer can be manufactured from the slowest computers called processors. I discovered how to map 32 real-world problems to 32 processors that were tightly coupled and that shared nothing. The general idea was to imagine Onitsha as comprised of 65,536 households and to move all 2 raised to power 16 households in Onitsha, Nigeria, into as many houses in Washington, District of Columbia, United States. I was in the news because I discovered how to move them in a proximity-preserving way that preserves the original nearest neighboring structure, namely, if Okonkwo and Okafor were nearest neighbors in Onitsha, then my nearest neighboring mapping would also preserve them as nearest neighbors in Washington, District of Columbia, United States. The word computer was first used in print 2,000 years ago. It was first used by the Roman author Pliny the Elder. The computer as we understand it today is the programmable supercomputer that was invented in 1946. In 1996, I was invited as an honoree to a celebration called the 50th anniversary of the modern computer. That celebration took place in Minneapolis, Minnesota. At that 50th anniversary banquet, a guest asked me, "Why were you honored for the development of the computer that was invented before you were born?" I answered, "My contribution to the development of the computer was that on the 4th of July 1989, I discovered the massively parallel supercomputer that is faster than the vector processing supercomputer. That is, I discovered the modern supercomputer of today that will become the modern computer of tomorrow. I discovered how to solve the grand challenge problem of supercomputing. This supercomputing problem was called a grand challenge because it was very complicated to solve it across a new internet. I visualized that new internet to be outlined by thousands or millions of identical processors, each akin to a tiny computer. That grand challenge problem was a century-old problem in mathematical physics. That grand challenge problem was in part published as science fiction by Louis Fry Richardson back on February 1, 1922. The January 11, 1946 issue of the New York Times loosely restated that grand challenge problem as a futuristic technology that would enable 100 computers to forecast the weather all over the world and to solve the toughest problem arising in mathematical physics. That New York Times article suggested that in the future, and I quote, the United States would be divided into blocks penetrating into the stratosphere. End of quote. Fast forward 43 years to the 4th of July, 1989. I invented how to divide the United States into 64 binary thousand blocks, each penetrating into the stratosphere. I discovered how to achieve a one-to-one mapping between those blocks and the as many tightly coupled commodity off-the-shelf processors. I figured out how to reduce 64 binary thousand days or 180 years of computing to merely 1 day of supercomputing. I discovered a new way of thinking about the new fastest supercomputer and about the supercomputer of tomorrow. I thought of it not as a computer per se, but as a new global network of tightly coupled processors that is a new internet and a virtual supercomputer. It is likely that Albert Einstein, who was then 66 years old and living outside New York City, read that supercomputer story that was printed in the January 11, 1946 issue of the New York Times. My supercomputer discovery that occurred 43 years later and on the 4th of July 1989 was the new knowledge of how I harnessed a new global network of identical processors or tiny computers that encircled a globe and harnessed it as a new internet. I discovered how to use that new internet to solve the toughest problems and the most important grand challenge problems that arise in extreme scale computational physics. That supercomputer discovery was science fiction to Albert Einstein. Thank you.
Insightful and brilliant lecture.
Thank you.
Insightful and brilliant lecture.